Now, let's take a look at how you form an image using a lens. The lens performs the same projection as a pinhole, which is perspective projection, except that it gathers a lot more light. You see a lens here, and let's consider this point in the scene P0. All the rays of light received by the lens from the point P0 are refracted or bent by the lens to converge at the point Pi. So Pi is where the point P0 is going to be focused behind the lens. And the bending power of the lens is defined by its focal length. Now, if you compare this with a pinhole camera, in the case of a pinhole camera, the only ray of light that would have made it through is this orange ray that I'm showing right here, which passes through the center of the lens. So the perspective projection model remains the same, except that the lens is able to gather a significantly greater amount of light. Now let's look at the relationship between the position of the point P0 and the position of its image Pi. Let's say that the distance of the point P0 from the lens is O, and the distance of the point, its image is I, that's the distance of the point Pi, then 1 over I plus 1 over O is equal to 1 over F, where F once again is the focal length of the lens. So for instance, if you use a lens with a focal length of 50 millimeters, and let's say the object happens to be at 300 millimeters, then the image distance is going to be 60 millimeters. So now, how does one find the focal length of a lens if that's not given to you? It's actually pretty easy. Once again, you have the Gaussian lens law. And in this equation, if you said O equal to infinity, which means if you use a source that is, or a point in the scene that is really far away and you image it, then O is infinity, then you see that F is equal to I. So by simply showing the lens an object that is really far away, such as the sun, a very distant point light source, and looking at where the image of that point source is formed on, say, a sheet of paper, the distance between the focused image and the lens is the focal length. Now, the bending power, or the focal length of the lens, is determined by a few factors. One is, of course, the material that the lens is made of. It could be made of glass, or it could be made of plastic. It has to be a transparent material. So the refractive index of the material determines F to a great extent, but it's also determined by the shape of the lens. The lens has two surfaces, curved surfaces, typically spherical surfaces. The radii of curvature of these two surfaces also determines the focal length of the lens. So now, with that in place, let's take a look at the magnification due to a lens. So once again, you have the object at distance O, you have the image at distance I, and the height of the object in this case is h0. And we want to know what is going to be the height of the image hi. So the magnification is defined as hi divided by h0. And if you look at these two similar triangles, the red triangles, this one and this one, you see that hi by h0 is equal to I divided by O, the image distance divided by the object distance. And so one can actually change the magnification of a lens system by using multiple lenses. So let's take a look at this two-lens system. So in this case, you have lens L1 and L2, and you have an object here at distance O1 from the lens L2. So this object is imaged onto this point right here. So it's focused onto this point here. We'll call that an intermediate image. That acts like a new object, if you will, and it is imaged by the lens L1 to get the final image right here. So the magnification of the complete system is a magnification due to lens L2 times the magnification due to lens L1. So that's I2 by I02 times I1 by O1. So you can see here that without changing the distance between the object and the image plane, you can actually move the lenses L1 and L2 around to change the effective magnification of the complete system. And so that really is the process of zooming. It's moving the lenses to change the magnification of a lens system. Now let's talk about the aperture of the lens. The aperture of the lens is the clear area of the lens that gathers light from points in the scene, and it has a diameter d. So in a typical lens, such as this one right here, you see that the aperture is implemented using what's called a diaphragm. So you can change this ring in the back right here, and what that does is that there's a set of blades that come together to change the diameter of the aperture. So from left to right, we're going from an open aperture to a closed aperture. And it's convenient to express the aperture diameter of a lens in terms of its as a fraction of the focal length of the lens, and that's called the f number. So you can define the diameter of the aperture as f divided by n, where n is the f number of the lens. And f, of course, is the focal length. So for example, if you had a lens with focal length 50 millimeters and an f number of 1.8, then the diameter of the lens would be f divided by 1.8, 50 divided by 1.8, which is 27.8 millimeters. So if you're looking at the f number as the aperture, as the way to represent the aperture, as you go from a fully open aperture to a closed aperture, the f number is going to go up while the diameter goes down. Now let's talk about the price we pay when we use a lens. Gathers a lot more light, but there's only one plane in the scene that is perfectly focused onto the image plane by a lens. And so let's take a look at our point O once again. This point O, distance O, is going to be focused at the distance I behind the lens. And let's place our image plane right there, or the image sensor right there. And so for this particular position of the image plane, there is exactly one plane which is going to be completely in focus. In fact, any point on this plane is going to be perfectly focused on this image plane. And this is called the plane of focus corresponding to your lens system. Now we have to ask what happens if you happen to lie outside of this plane of focus. So let's consider this point right here, which happens to be at a distance O prime from the lens. Since it's closer to the lens, its image is going to be formed behind the image plane. In other words, the light that the lens receives from this point is not going to end up being a single point on the image plane, but rather distributed over a circular disk on the image plane. It's going to be blurred. And this is called the blur circle. The blur circle has a diameter, let's say, equal to b. We want to figure out what this blur circle diameter is for any given position of the object in the scene. So for that, we use these similar triangles, the small orange triangle here and the large one. These are similar triangles, and we know that b divided by d is equal to this distance right here, which is I prime minus I divided by I prime. And so we see that the blur circle diameter is proportional to the diameter of the aperture. You use a lens which deviates from a pinhole camera more and more, which is larger and larger aperture, you're going to end up with a greater degree of blur for points that lie outside the plane of focus. So the blur circle diameter is proportional to the diameter of the aperture and therefore inversely proportional to the f number of the lens. So now in this expression right here, you see that we have the image distances I prime and I. We'd like to express this in terms of the object distances O prime and O, because that's what we have at our disposal. We want to know what happens when we move things away from the plane of focus in the scene. So for that, we use the Gaussian lens law again. We can write the Gaussian lens law for lens equation for the focused point. We can then write it for the defocused point. And from these two expressions, we can get an expression for I prime minus I in terms of O minus O prime. Substitute in the expression for the blur circle, and we get this expression right here. The diameter of the blur circle is f squared divided by n. N, once again, is the f number of the lens. F is the focal length. And on the right side here, you see O and O prime. The distance, O minus O prime, is the distance of this point from the plane of focus. Okay, so how do we focus an imaging system? So here you see an out of focus, defocused imaging system. Here's the object that you want to image, but it's being imaged behind the image plane, therefore creating a blur circle right here. So the obvious thing to do to focus this imaging system would be to move the image plane. That's one way to do it. Or you could move the lens itself, thereby changing the Gaussian lens equation and getting the point into focus. Or you could change both. You could move both the lens and the image plane. For that matter, you could also move the entire camera system towards or further away from the object so as to bring it into focus.